Hooke's law says when a force is applied to a spring, the displacement of the spring is proportional to the restoring force in the spring. And restoring force just means because if you pull on a spring, it wants to come back to its original shape. So we're talking about that force that really wants to pull back. It's a restoring force. And we're going to see that it's Fs, the force felt in the spring, is equal to negative Kx. And note that it's negative Kx. Okay, it's negative Kx because Fs is a restoring force. It's pulling back opposite the direction of the displacement. And let's take a look at our next diagram to see more about this. But again, if you pull the spring to the right, it's going to want to pull back to the left. That's restoring force, which is where that negative sign is coming into play. Now, our dimensions are going to be newtons, obviously, because force is measured in newtons. And we can tell because the units of K are newtons per meter, and the units of displacement are meters. So our dimensional analysis checks out, right? Those cancel, giving us newtons equals newtons. In this diagram, what we want to really do is take a look at what happens as a spring moves. And what we're going to see is that if the spring's original position was right here's the equilibrium state, meaning the spring is not stretched at all, there's no displacement, and therefore there's no force being applied to it. If it's pulled to the right, like the spring, right, I take my arm and I pull the spring all the way to the right, which way does the spring want to pull back? Well, when it's pulled to the right, this is the situation. The spring, restoring force, wants to pull back to the left. This is like your Fs, your restoring force, the pull back. And notice that the displacement, though, is to the right. And see that those vectors, this is to the left, this is to the right, and that's where that negative sign is coming from in Fs. And then down here, the same thing occurs. When the displacement is to the left or the spring is compressed, now the spring wants to shoot off to the right. It's going to push back to the right. So when the displacement is left, the force is to the right. Notice this here is where it's at maximum displacement all the way to the right. This is at the equilibrium position. This is at its maximum displacement all the way to the left. And if you pulled this all the way out here and let go, it would sit there and just oscillate back and forth between these two positions. And realistically, over time, it's going to come to settle out because we know that there's friction involved. But hypothetically, if there were no friction, this would simply oscillate back and forth between these two positions, between max displacement here and max displacement down here. Okay, again, about this center line or this like origin where the spring is in a state of equilibrium. There's no force acting on it, force equilibrium. Example 1 says a spring is stretched from its free length of 100 centimeters to a length of 160 centimeters. If the applied force required to stretch the spring is 120 newtons, determine the spring constant. So let's take a look at what we have here. Well, we've got the free length of the spring is 100. The actual length is 160, and we know that x represents the change in the length. So final minus initial, okay, or stressed length minus the free length there, is going to give us a displacement of 60 centimeters or 0.6 meters. We know that the force being applied here is 120 newtons, and that's pulling it to the right because there's no sign there, it must be positive. That means that the restoring force felt by the spring wants to pull back to the left. So the restoring force is a negative 120 newtons. And again, we're in a condition where here's the spring, here's the mass here, okay, and it's being pulled to the right. So that's the original length, and now we're at a length of, say, like this. Okay, and this was the length of 100 centimeters. And between here and here is a length of 160 centimeters. Therefore giving you that delta x value, that x value of 60 centimeters or 0.6 meters. So since the applied force is to the right, this is Fp, I'm pulling to the right. Which way does the spring want to pull? The spring wants to pull back to the left. So the restoring force, Fs, felt by the spring is negative 120 newtons. So we go ahead and take a look at our formula. Fs equals negative Kx, that's Hooke's law. We want to figure out what the spring constant is, so solve for K. So let's divide by x. We'll get Fs over x equals negative K. Well, if that's negative K and we want positive K, just divide by negative 1, giving it negative Fs over x equals K. Well, let's go ahead and plug in. Negative in the front, and then negative 120 newtons over the x value of 0.6 meters gives me, well, we have a negative here and a negative here, making that positive. And look at that. K's got to be positive. It's a spring constant. You can't have a negative spring constant. So we take the negative 120, multiply by the negative out in front, and then divide that by the 0.6, giving us a spring constant of 200 newtons per meter. And again, let's make sense of this. What this means is the following. It would take 200 newtons of force to stretch this spring a distance of 1 meter. That's what your spring constant is saying there. Now let's take a look at what happens when a spring is in some sort of oscillatory motion. And in this case, we're going to neglect friction to help us here. So imagine that you have a spring and you pull on it and you release it. So you pull the spring. So here's the original length of the spring. It goes to here. So we could say this is like the original length. You pull on the mass until it gets to here and then you let go. It's going to sit there and it's going to vibrate like we just said. But here's the thing. When you pull on the spring all the way out to here, that's when there's going to be a maximum amount of force in the spring until you let it go. And then what's going to happen is the spring is going to get compressed. It's going to get compressed, it's going to get compressed, and that's going to be here at this stage now. And when it's at this stage, the spring is not actually compressed or stretched. It's in its equilibrium. So this is the only time that the force is going to be zero. The force, of the spring is going to be zero. Now, when the force is zero, there's no acceleration. So technically right here, the object has no acceleration. And here's the reason. Right at this point here, the force of the spring is pulling to the left. That's the spring pulling back against the mass. Well, that's the maximum the spring is going to pull with, because you're not extending the block out to here, so you can't pull back any further. So again, we have a limit to where we're extending the block to. Now, because of that, that means that since this point in time is when it's going to feel the most force pulling left, it's also going to have the highest acceleration at this point in time right here. But if you notice, this is like you're holding it and then you let go. So the velocity is currently zero. You're holding it there, you're holding it there, you're holding it there, and then you're going to let go and it's going to start to move. Now, it's going to move and it's going to pick up velocity. It's going to keep gaining velocity. It's going to get faster until it gets to here. But when it gets to here, it's going to start compressing the spring, which means it's going to slow down. The spring is going to now push against the mass, it's going to slow it down. And that's why now suddenly in this case, the acceleration is to the right. So here, the acceleration and the force both pull to the left, because again, the force wants to pull it back, therefore the acceleration is left. Right here, there is no force, so there is no acceleration. But once the object gets compressed all the way here, now the force wants to push to the right. The spring wants to push back that way, so the acceleration is also to the right. And that's at a maximum acceleration, but to the right now. So we're seeing that the acceleration was left here, then suddenly the acceleration is to the right. Well, the only way acceleration can go from negative to positive is for acceleration to be zero at some point in time. That's in the midline here. That's why that part makes sense. Now, let's take a look at the velocity, though. This is a little more confusing. Here the velocity is zero because it's at rest. Here it's going to pick up speed, pick up speed, pick up speed, pick up speed, pick up speed. Then at this point in time, it's going to start to lose speed, lose speed, lose speed, lose speed, lose speed, and then it's going to become zero. Again, velocity is zero. So this midpoint here is when the velocity will be a max. So you pull the spring out to here, you let go, and you can watch this in slow motion if you wanted to. It would pick up more and more and more and more speed, and then it would slow down and slow down and slow down until it gets to here and it stops. That's right here. When it stops, there's no velocity there again. Okay, but the force is to the right, and it's the maximum force allowable, but to the right. So the acceleration is to the right. Then what's going to happen is it's going to go through the same cycle again. Now the velocity is going to be pushing to the right. It's going to pick up speed, pick up speed, pick up speed, pick up speed till it gets to here, and then it'll start to slow down again until it gets to its stretch length, and it'll stop again here. That's right here, where it stops, and then it'll pull back to the left, and it'll continue this motion. But at this point in time right here, the velocity is at max again, just like it was earlier, but this is a maximum velocity that would be to the left. So this might be like negative 10 meters per second right here. But when it's right here, since it's going to the right, and you can see that, look at the tail here, it's trying to show you that it's moving to the right, the velocity is a max, but to the right now. Again, because it's at equilibrium, though, there's no net force acting on it, and there's no acceleration here. Until it gets all the way to the right, and then once it gets all the way to the right, we're back to the beginning. And the spring wants to pull left again, so we're back to the force being left, or the max force being to the left. Same thing with acceleration, left again, but it pauses again. That means the velocity is zero right here. Now, the positive x and negative x just represent the deviation from the actual equilibrium position. That's the x that we look at in our formula. Remember that this here, from here to right here, is x. That is the actual change. That's x right there, and that's the positive x. That's this right here. And in this direction, this is just saying that x is to the left, or x is negative in this case. And finally, we're going to take a look at a mass spring versus a simple pendulum and see the fact that they are analogous to one another, these two situations, which is pretty amazing to think about because they look very different at first. Well, here's what's happening. When this spring is stretched all the way to the right, the restoring force wants to pull back and pull it back to here and then go through this motion again, like we kept saying. And that's the motion, all the stages again that we looked at a moment ago. But compare this to a pendulum. It's the same thing. Take your hand, lift the pendulum bob till it's here. Well, right now, what does it want to do? It wants to go back to the middle. Gravity wants to pull it back. So it has a force acting that's going to pull it to the middle. Remember, gravity pulls down, but a component of gravity is always acting in that direction. Remember, you can break up gravity like we did on the inclined plane. So part of gravity wants to pull it back to the middle. So in this case, the spring was the restoring force. Now there is no object besides the actual weight, okay, or gravity being the restoring force here. So the mass of the pendulum itself is what pulls it back toward the middle in this case, not the spring. Whereas here, this mass doesn't really affect what's pulling back. It's the spring that's pulling back. Remember, the spring pulls it to the left here when it's pulled right. Well, when this pendulum is pulled to the right or lifted, and you let go, it suddenly starts to move to the left because of gravity. And then here at the bottom, it's at its maximum velocity, and then it starts to slow down again and come up to the top. And then it stops, it pauses. So there's no velocity when it gets up here, just like there was no velocity when the spring is compressed. And then suddenly the pendulum starts to slide back. It gets to the bottom, it's at a maximum velocity. Well, that's when the spring mass system was at equilibrium, at its maximum velocity, until it then continues to go to the right, and it eventually stops up here, which is like this spring continuing to move to the right and then stopping. So these 5 stages that we looked at a moment ago are completely analogous to each of these 5 stages. So maximum amplitude, maximum amplitude. Here you're going to have maximum force and acceleration. Here, maximum force and acceleration. Here there's going to be no velocity. Here there's going to be no velocity. And we can go through each of these situations just like we did in the last problem. So take a look at your last problem's chart here and see how each one of these are analogous to the scenarios we see at the right. Now notice though, instead of a positive and negative x, you're going to have your theta value as your displacement. This is an angular displacement. This is a linear displacement. Your homework for this section is from 2 different pages in chapter 12.